Good morning, folks. Sorry about the delay. Technical problems. Let's wait a few moments till everybody comes in. How are we doing? Questions while we wait? Somebody's asking why the series 1 over n log n diverges. You can work that out easily using the integral test. The test works very well here. I'll let you work that out. Shen is asking a Webwork question. Find the error in approximating ln of secant of negative 0.2 by its 4th degree Taylor polynomial at a equals 0. You need to find the 5th derivative. And what is z? Well, you're correct that you need to find the 5th derivative. And what is z? We don't know what z is. Z is some number between negative 0.2 and 0. In fact, it's a strict inequality, but whatever. And that's it. That's all we know about z. But when you look at your 5th derivative, you'll probably be able to bound it using the fact that you are in this bounded interval. So, I mean, as Shen is suggesting, you're going to use a Lagrange remainder theorem. Absolutely. Nintendo here is asking, can I use a comparison test for that? It's going to be difficult. For the first series there, it's going to be difficult to use the comparison test. Integral test is what you want to use. Avery is asking, what's the point of changing the start of the series from 0 to 1? It depends. It depends. There's no answer to that. Depending on what you want to do, it may sometimes be useful to change the starting point from 0 to 1. In particular, if you have a general term that is only valid for 1 and above and does not work for 0, then that might be a good reason to do that. Bryn is asking, when will Webwork 2 be out? We haven't actually done any work related to Webwork 2 yet, so I'm waiting until we do a bit. Probably by the end of the week. How do you find distances between two planes? Well, I mean, you should know that from 133. If you have two planes, first of all, the two planes better be parallel. If your two planes are not parallel, then they intersect and the distance is 0. So if the two planes are parallel, meaning that they have the same normal vector, you're going to take a point on one plane, a point on the other, and look at the vector joining these two, and then you're going to project that onto the normal. And look at so the distance between the two planes is going to be the length of the projection of V onto the normal, right? You're going to project that onto this, and it's going to give you exactly the length, the distance between the two planes. Amar is asking for the series pi sine of n plus 1/2. I mean, I suspect you mean sine of n plus 1/2 pi over 1 plus root n. I'm going to assume that that's what it is, even though that's not what you wrote, because that's the more important question. Notice that let's work out what this is. When n is 0, this is sine of pi over 2, which is 1. When n is 1, this is sine of 3 pi over 2, which is -1. When n is 2, this is sine of 5 pi over 2, which is 1. And you see what's happening, right? This is actually the same as -1 to the n. So this series is really -1 to the n over 1 plus root n. It does not converge absolutely, and I'll let you test that. You can do a limit comparison with the series 1 over square root of n, but it does converge conditionally. It is an alternating series, and you can make sure that it satisfies the hypotheses of the alternating series test, and you get conditional convergence. Shen is asking, how can we know it's exact when since z is random here? Well, that's the thing. You never get an exact error using the Lagrange multiplier, the Lagrange remainder theorem. What you do get is an upper bound on what the error can actually be. And that's going to be good enough. Because if you make the upper bound less than whatever value you want, then of course the error is going to be less than that as well. Vivian is asking, when you're using the alternating series test error estimate, is the real value between the sum minus the error and the sum plus the error? Short answer, yes. Yeah. Right, because what you're really showing is that whatever the sum is minus the approximation is less than or equal to the next term in line. And so this is the same as saying the sum minus the approximation is less than the error, but bigger than negative of the error. So now add a to both sides. Your approximation minus the error, less than the sum, less than the approximation plus the error. There it is. Anna Maria is asking, can you explain why when you differentiate a power series you need to change the index from 0 to 1? You do not, and I have not done that in class. You do not need to change. You may change if the situation warrants it, but you don't. Right? If you have a power series and you differentiate term by term in the interval of convergence, this is what you get. Period. That's the answer, and everybody's fine with that. However, when n is 0, the first term is 0. So you may decide to start it at 1 if you want. You don't have to. Sometimes it's useful to do so. Sometimes it's useful to leave it at 0. It depends on the situation. Renji is asking, so the initial V here is free to choose? Absolutely. Absolutely. You're going to choose 1 point here, 1 point there, and take the vector between the 2 points. What if we want the distance between 2 points on 2 planes that are not parallel? Well, if you just want the distance between 2 points, then it's just the length of the vector joining those 2 points. If instead you wanted the distance between the 2 planes that are not parallel, then the planes have to intersect and the distance is 0. Amar is asking, whenever we get an alternating series with sine or cos, we need to test for convergence. We need to change it to another form. That is not the case. Here I'm pointing out that in this special case, it's the same as the sequence -1 to the n. If you had sine of n instead, just n, then none of this would follow. Blue Pill is asking, if the question asks for the exact error, we just have to subtract the calculated value from the exact value. That's exactly it. That's the actual error. And I think that answers Shen's question as well. Tony is asking, use a series to approximate the integral from 0 to 1. One over 1 plus x to the 4. Correct to 2 decimal places. We're not going to do it, but you know exactly how to do it. You could actually integrate this with a lot of work. Let's not do it. Instead, let's approximate, and you're going to find the Maclaurin series for this function. You're going to show that the interval of convergence is -1 to 1. So here you're fine in the interval of convergence. You're going to integrate term by term, and what you end up with is an alternating series. And you can approximate that alternating series using the result at the end of the alternating series test that we proved, and you're good to go. Shen, exactly right. If you have just sine n, you don't have an alternating series. So the alternating series test will not apply here. Renji is asking how we find the Maclaurin series for sine of x to the 4 from scratch. Well, I mean, there are two options. There's the usual way. You can always take the derivative. Right, so function at 0, derivative at 0, and so on, form those two columns and work out. Or you can find the Maclaurin series for sine x and then plug in x to the 4 instead of x. Can we use Lagrange for the question up there? The problem with Lagrange remainder is that you need the derivatives. Here, we're going to do a trick where you're going to evaluate the Maclaurin series, but not by finding derivatives, just by a nice trick, the Taylor series, the geometric series business. So that's why Lagrange remainder for that probably not useful. I mean, at least not immediately. You would need to do a lot more work to use a Lagrange remainder for this question, and I mean, that's going to defeat the purpose. Blue Pill is asking, will practice questions for topics not in last semester's textbook be posted on my courses? Well, I feel that everything we've done so far is in last semester's textbook. If you don't have the textbook we're using, I gave a link to free online resources where you have a bunch of free calculus textbooks, which will cover the material from now on. So you can have a look at that. Renji is saying by taking the derivative for sine of x to the 4, you get 0 all the time. I claim you do not. You get 0 for a bunch, but not always 0. No, you still center of 0, that's fine. If you want to use Lagrange, we must find the power series of the function. Well, you must find it from those two columns thing, right? Function, derivative, second derivative, and so on, right? Function at 0, derivative at 0. In other words, to use Lagrange remainder, you need to understand what the nth derivative is going to be. Very nice observation there, Quinn. All right. Questions? In any case, I suspect for sine of x to the power 4, I suspect the fourth derivative is not 0. You probably don't have to go until the 12th power. I'm pretty sure the fourth derivative is not 0. Lyra is asking for the Taylor series of e to the x squared about a equals 2. You know how to do that. You can do that very easily. Yeah. I mean, you can start by finding the Maclaurin series for e to the x. You know that it converges for all values of x. Then replace x with x squared. And then replace x with x minus 2. But then, well, I mean, yeah. So, well, maybe not the way to go. There'll be a little fiddling around there. Maybe the best way is to do those two things. Yeah, brute force. All right. I feel that that's enough questions. Let's get to work. We can answer some questions at the end if you still have some. Our goal for the rest of the semester is to extend the notions of calculus to higher dimensions. You can do composition for that question. You can. It's just that it's going to be slightly. It's not just immediate, right? I mean, what you're going to get is the Maclaurin series for this function, But that's not the one you want. Right? That's not the function you want. You just want this one. So you're going to have to get rid of these other parts, and that's a little messy. It's not impossible. It's not impossible to do. It's just, it's not immediate. That's all I'm saying. Right. So we want to extend the notions of calculus to higher dimensions, differentiation, integration, and so on. Let's start with something simple. Graphing. It's nice to have an idea of what our function looks like. And graphing in several variables, students find that difficult. But there's a nice way to bring everything back down to 2 dimensions. So suppose you've got a function of 2 variables, f of x and y, right? I mean, let's take an example here just to get us started, right? This is some function of x and y. If you plug in a value of x and a value of y, it spits out a value for z, right? So this is really an extension of y equals f of x. Here you've got a third variable, z equals f of x, y, right? For any value of x and y you plug in, you get some height value of z. Now, we want to graph this. Our goal is to graph this, understand what the graph looks like. And graphing in 3D, we don't know how to do that, but you know how to graph in 2 dimensions, right? If I give you y as a function of x, you know exactly how to do that. We're going to make use of this knowledge. I'm just saying it's an example here. It's just an example. This is just an example. Z equals x squared plus y squared. We're going to make use of our 2D knowledge to help us graph in 3D. Let's move away from that for a moment and imagine that I asked you to draw a mountain. Just take a moment to draw a mountain. I know what you're thinking. You may be thinking something like this. I'm no Bob Ross, but it's all good. Well, that's not what I meant. Let's instead draw a mountain from a bird's eye point of view. So imagine you were flying above this mountain range in a plane. How would you draw that mountain? How would you describe the fact that you have these kind of 2 peaks here, maybe a third peak there, some sort of valley down below? Right? So here you've got this peak. And there you've got this other peak. and then maybe some sort of valley in between, and so on and so on. I mean, maybe you had a third peak there at some point, right? Where you could label how high each of these curves were. These are known as contour lines or contour curves. If you pick up an old road map, nobody has those anymore, but when I was young, before the internet, we had road maps. And on road maps, if you were going through mountains, you would have these contour lines telling you how high you were. Right? So what I'm saying here, right, you had this peak, and then this was that height, and then at this height you had these two things happening, and then at another height, this and that and that, and so on and so on. Right? You have these contour lines which help you to graph the function. These contour lines are the intersection at different heights z. Right? How high is that? Well, I mean, at maybe z equals 1,000 feet, you just touch this peak. And at z equals 900 feet, well, you have this curve that goes around that peak. And then at 800 feet, well, you touch this peak, and then you still have that, and so on and so on. Right? So that's the idea of contour lines. It's the intersection at height z of your curve. So contour lines, also known as level curves, right? It's curves that are at different levels of z. And now, imagine that you had your mountain and you cut it at different levels. And imagine these as now building blocks, very much like a Riemann sum. Imagine putting your mountain back together with these building blocks, right? So the curves cut at every level, and then you would just build your mountain back up if you had these. So you see that if you have a graph, you can work out the level curves, and if you have the level curves, you can put back your map together. And these level curves are just two-dimensional curves. They are curves in the xy plane. Tony is asking, if we have a cylinder, will the contour lines overlap from the top view? Not sure what you mean here, but suppose you had a cylinder. Right? If you fix any height c, the cut would just be a circle. So you could what's the word I'm looking for here? You could build your cylinder by stacking circles one on top of each other. Circle for the base, circle on top of that, blah, 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 until you reach the height you want. Let's take this example, this simple example here that I was suggesting. Let's talk about the level curves. The level curves are if you fix some height z. Let z be fixed. Let z be a fixed constant. The level curves are the family x squared plus y squared equal to z, x squared plus y squared equal to c. Exactly. Mathan says that you see this in geography textbook and it's used for physical features. Absolutely. Absolutely. Yeah. Like I said, on road maps you had that. On some globes you had that as well. But really in essentially any geography textbook, this is used to illustrate how high everything is. And it gives you an idea of the view from the side as well, right? This has one higher peak here, a medium peak there, a lower peak there, and so on and so on. I've rubbed it off now, but you know what it is. If z is constant, could you just ignore the z-axis entirely and represent it from x and y? Well, that's exactly it, right? These level curves now are just functions of x. So, right, I mean, at least theoretically, you could solve for y as a function of x, or perhaps just implicitly, but this is a family of curves in the xy plane. So let's draw these in the xy plane. What is this family of curves in the xy plane? When c, first of all, convince yourselves that c cannot be negative, right? Because the left-hand side is bigger than or equal to 0. There are many questions here. Wayne, that's very funny. If z is constant, yeah, right. Is this the same question as the plane? If it is, isn't a infinite plane, circle, circle. Ran, I'm not exactly sure what you mean here. This is not a plane, right? You recognize these as circles. If c is 0, the only point that gives you 0 is if both x and y were 0. So we have a point at the origin. And then for any c bigger than 0, you have circles of radius root c. So you have this family. You have this family of circles centered at the origin. Let's make use of this observation to help us graph the function in 3D. And while we are graphing in 3D, we're actually going to graph everything in 2D instead. Well, you could, first of all, there's no integral here, but yeah. We're going to get to angle and radius momentarily, well, I mean, not today, but later on in the course, it is an important aspect that we'll encounter. Right, so, but now what we want to do is graph z equals x squared plus y squared. And we're going to graph it always in 2 dimensions. Even though our graph is going to be in 3D. You'll see how we're going to do that. Take y to be 0. If y is 0, z is x squared. If y is 0, you are in the xz plane. So in the xz plane here, you have the graph z equals x squared. This is just a regular 2-dimensional graph. You know what this looks like. Z equals x squared. It's just a parabola. (2D), you're very used to that. It's all good. Repeat. Take x to be 0. If x is 0, you're looking at z equals y squared. So in the yz plane, when x is 0, again, it's just a parabola. All right. Well, now we have these 2 parabolas. How do we bring everything together? If you were to cut your object at some height c, if you were to cut your object at some height c, you would get circles. You put all of this together using circles. It's a terrible example there. Terrible. You put everything together using circles. So you get this kind of bowl shape. There it is. So we've always graphed in 2D in the xz plane, in the yz plane, and then level curves, which are themselves 2-dimensional. Right? Imagine, if you will, pulling, right? Imagine that these were all tied together using some sort of chain. And then if you were to pull that up in the direction of z, right, they would just pull up, you know what I mean, do you? Right, imagine pulling these up like these planters that are made out of chain. Let's take a few more examples. How are we doing here? Right, again, let me point out here, right, we're really saying if you take any point xy in the xy plane, you go up to a z value using this function, right? So that's really what we're graphing here. If If x and y are the point 1, 1, then you go up a height of 2. And so on and so on. Consider this. Let's start by asking the question, what are the level curves here? Right, what are the level curves? So this is the function z equals that. So if z is c, we get 2 minus x squared minus y squared is equal to c. If you interchange, we again have circles, in this case of radius square root of 2 minus c, center at the origin. Vinit is asking, can we level down z to 2 minus z? And then just have those circles. You could, there's something that could be done here. You could make a change of variables. Very nice. But you don't really need to. It's not going to make anything any simpler. The point is that these are still circles centered at the origin. Let's draw this object, making use of that. Right, what are we graphing? Z equals 2 minus x squared minus y squared. So again, absolutely, Ahmad is, no, you're right. Ahmad is suggesting that it's the same thing, except it's flipped and moved up. That's exactly right. Let's draw it in the xz plane when y is 0. You know what that looks like. It's a parabola coming down, starting at 2. And coming down. And in the yz plane, when x is 0, it's again a parabola, starting at 2, coming down. So you have this sort of skeleton, if you will. Avery is asking, is this going to build on the previous unit? Will they intertwine, or are they completely separate? They are essentially completely separate. Almost entirely completely separate. Except, as you may imagine, we ended with Taylor's series of a function of one variable. We're going to extend that to Taylor's series of functions of several variables. That's the only way they're going to be connected. Right, so we have this sort of skeleton for our function that we were able to graph in 2D, right? When y is 0 and when x is 0. And now the question arises, how do we put everything together? How do we fill in the skeleton? Well, at every height 2 minus c, if you're cutting, you end up with a circle of radius root 2 minus c. You are putting everything together using circles. So you have this sort of dome shape coming down. Benita's asking, what about cusps and loops? We're going to see that in more detail when we get to polar coordinates. We're going to discuss that, but probably in about 2 weeks. How are we doing here? Right? So graphing in 3D, not that difficult, right? You graph it in 2D and then you put everything together. Let's take another example. Again, let's start by asking, what are the level curves here? Amar is asking, the circles are getting smaller towards the top, so how come the radius remains constant at root 2 minus c? Remember that c was the level z at which we're making the cut. Right? So if we're making a cut here at level C, which is very close to 2, let's take C to be 1.5, 1.5, then this is 2 minus x squared minus y squared. So this is really x squared plus y squared is equal to 2 minus 1.5 or 1/2. Right? So you see that the radius is getting smaller the closer you are to 2. Right? In general, it was x squared plus y squared is equal to 2 minus c. If c is very close to 2, the radius is very small. Exactly as it should be. So again, question is, what are the level curves here? The level curves are this, or which you recognize to be ellipses centered at the origin. Let's graph the function. So again, right, what are we graphing? We are graphing z equals square root of 4x squared plus y squared. Let's graph it in the xz plane. If y is 0, z is the square root of 4x squared, which you know to be 2 absolute value of x, right? Because this is always positive. So 2 root x, you know what that looks like. Looks like this in the xz plane. In the yz plane, when x is 0, you have z equals square root of x squared, which is absolute value of y. So you know what that looks like in the yz plane. Looks like this, but not as, it doesn't increase as fast, right? Here you had 2 versus the 1. So not as steep. And then you put these together, right, at every height c, you put this together. How so? With ellipses. So you have some sort of cone shape where these are ellipses. Very nice. How are we doing here? Consider this. Let's graph this. What does the graph look like? Of course, you recognize that there is no y here. It's the function z equals x squared. There's no y. How does that translate into the graph? Well, let's do what we were doing before. Let's graph it in the xz plane. If y is 0, there is no y, so it doesn't affect this. If y is 0, it's just z equals x squared. So this is just the parabola in the xz plane. It's this parabola when y is 0. But when y is 1, it's still the same parabola. And when y is 2, it's still the same parabola. And so on and so on. Imagine taking this parabola, the original parabola, and dragging it in the direction of y. And then backwards as well. This is your function. It's this parabolic cylinder, if you will, resting on the y-axis. Let's repeat. Renji is asking, but didn't we connect the skeleton with the function before? Correct. But here there is no real skeleton. The only skeleton was the z equals x squared. So shouldn't you connect the parabola with z equals x squared? Well, I mean, look, see, observe what happens if you do that. If you were to cut your parabola at z equals c, right? Because it still makes sense. It still makes sense to ask the question, what are the level curves here? And what are the level curves? The level curves are x equals plus or minus root c. So what is x equals root c? Well, you're thinking to yourself, it's a point, but it's not really a point because there are no y values mentioned here. So z equals root c, right, in the xy plane here, z equals root c is a straight line, a straight vertical line. So in the direction of y. So how does that translate to here? You had your parabola, your skeleton, if you will, and then you have these straight lines in the direction of x. I mean, parallel to y. So put these together using straight lines parallel. Terrible. That wasn't parallel at all. So these straight lines parallel to the y-axis. Yeah, so as Renji suggests, we should connect these parabolas with z squared equal to c, or x squared equal to c, or x is plus or minus root c, which are really just straight lines. But I think this idea of dragging is also very nice. I don't know. Two ways to view it, two equivalent ways, because it gives you the same thing, right? Let's repeat. We're looking at z equals cos y. And you're thinking to yourself, there's no x here. Let's draw it in the yz plane. Right? It's just a regular function here where z plays the role of the y-axis and y plays the role of the x variable. You know what that looks like. This is z equals cos y in the yz plane. But there is no x variable again. So you can think of dragging this in the direction of x. If you want to redo it as we did with the contour lines, nothing wrong with that. We ask ourselves, if z is equal to c, we have cos y is equal to c. C is fixed here, so there are only a few values of y which make this true. And so you're going to get y is the inverse cos of c, a fixed value of y. So in the xy plane, y equals arc cos of c is just a straight line parallel to the x-axis. So you draw these straight lines parallel to the x-axis. Is that parallel? Right, so that's the idea of dragging these along the x-axis. Yeah, I don't want to draw anymore now. I'll just mess that up. But you see the idea, right? So that's what this looks like. It follows the graph of cosine, but coming out towards us something like this. Can you repeat why they are parallel? Right, what are we looking at? We're looking at y equals inverse cosine of c for any fixed c, right? So what are these? These are straight horizontal lines, right? If y is 2, well, that's not going to happen here, of course. Well, no, well, anyway, if y, let's take obvious examples. If y is pi over 2, or if y is pi over 3, or if y is pi, that kind of thing, right? These are horizontal lines. So there it is. These are all horizontal lines. They're all parallel. They're all parallel to the horizontal line, y equals 0, which is the x-axis. So they're all parallel like this. Questions here? And those are level curves. Yes. Right here, y equals inverse cos of c. These are the level curves. Absolutely. Horizontal lines, correct. So y equals inverse cos of c is a top view of 3D graph. Okay. Let's call it that. If you were to flatten everything, yeah, absolutely. Now, this idea of level curves extends to higher dimensions. If you have W as a function of x, y, and z, so now we have a four-dimensional object, essentially impossible to graph. Vinit, possibly we're not going to discuss loops though. If you have a function of, so W equals a function of three variables, you understand what that means, right? You've got this fourth dimension, and for every point x, y, z in 3 space, you get some height coming up in a fourth dimension. You may be able to use colors as the fourth dimension. That's a very nice way around that. But the point being that we have this idea, right? Again, even though we're not going to be able to graph it, you understand that there's a height coming out for every point x, y, z. To help us graph, although we're not going to graph, but to help us understand what the function would look like, we can use the same idea here. Imagine cutting this function at different heights. In other words, f of x, y, z equal to c. Perhaps, theoretically, you might be able to solve for z as a function of x and y. So what you would get is something like this. You would get a surface. These, in higher dimensions, are known as level surfaces. And let's take an example. Consider this, right? So for every point x, y, z, if you plug in any point x, y, z to this, it spits out some height w. We're not going to graph this, but we can ask the question, what are the level surfaces? And if you let w be c, what do we get? We get 3x plus y minus 2z equal to c. And you recognize this as the equation of a plane. Thank you, Tony. So if you were to cut your surface, if you were to cut your object at different height w's, you would get planes. So this object is built by stacking planes one on top of each other in the direction of W. There it is. All right. Now that we have an idea of how to graph functions, you know, again, it's just a rough sketch. Nothing too precise is happening here. Let's think back to Cal 1. And what was the first thing we did in calculus? We introduced the notion of limits. And in one variable, on the whole real line, there are really only two ways to get to a point A. You can get to A from values bigger than A, and you can get to A from values less than A. This gave rise to limits from the right and limits from the left, respectively, and that was very easy to deal with. If we want to generalize the idea to higher dimensions, to the xy plane, say, if you fix a point AB, well, I mean, you can get to AB this way, that way, here, there, or infinitely many other ways. And that illustrates the difficulty of extending the limit definition to higher dimensions. There isn't just two ways to approach a point now. A point can be approached by infinitely many different ways. In the one variable case, we would say that the limit exists if limit from the left and limit from the right exist and are the same. Here, the limit is going to exist if the limit from every single curve going to that point exists and is the same. When I say dimension, right here I was in R1. On the whole real line, this had dimension 1. Here, we're dealing in R2. A point has two coordinates, 2 dimensions. So Brun is asking, if we move to the 5th dimension, there will be a bigger infinity of possibilities to go to a point. It's a good question. It's a good question. It's a good question. A question which we will answer in Math 180. I will invite you to take that class in the fall, but we will answer that. Spoiler alert. Do I want to spoil it? Let's not spoil it. Math 180 is where you'll find the answer to that. See you in the fall. Yeah. So all we're saying here let's not introduce complex numbers here, but yeah, let's not introduce complex numbers quite yet. So again, the point was, in R1, really only two ways to get to A. Here, if you're moving to 2 dimensions, if you're moving to R2, you already have infinitely many ways to get to a point. So you see the issue. How can you guarantee that every curve going to that point gives you the same limit? You're of course not going to spend time calculating a limit on every single curve, every single path leading to that point. That would be preposterous. Surely there's an easier way, and there is. The easy way, believe it or not, is the generalization we get from R1, the Epsilon-Delta definition. We say the limit as xy goes to AB of f of xy is L if epsilon greater than 0 is given. There exists a delta greater than 0 such that if the distance between these two things is small, but not 0, then your function is close to L. Let's understand this. Well, first of all, it's an immediate generalization of the Epsilon-Delta definition in Cal 1 that you know and love. Let's see what this means from a graph. Suppose you've got this function hovering above, z equals f of xy. And if you take a point x, so if you take a point AB, we're saying that the limit exists if your function can be made very close to L by taking points xy very close to AB. So if you take points xy very close to AB, if you take a disk of radius delta, so if you take any point xy in this disk, this gets mapped via your function to something very close to L. How close? Epsilon close. There it is. Let's take a few examples. So L is the distance to Z. No, what we're saying is if this limit exists and is L, right? Because we're saying f of xy is essentially equal to L. So L is the height of Z, if you will. Let's call it that. Not distance, but the height. All right, let's consider this limit. Does this limit exist? And if so, what is it? Well, again, from a graph, what are we saying? Here we're going towards the origin. So if the limit exists, the limit has to be the same from any direction. Any way you get to the origin, the limit should be the same. So let's investigate a few paths. Let's try to see what is happening. Suppose we go to the origin via the x-axis, right? What if we go to the origin this way? When y is 0. If y is 0 here, your function, this is 0, this is 0, your function is just x squared over x squared. And what is that limit? That limit, right, this cancels out, and that limit is just 1. So if the limit exists, it has to be 1. Let's repeat and ask the question, what if we went to the origin on the y-axis? If x is 0, that's 0, that's 0, you've got a negative y squared over y squared, whose limit is negative 1. These are not the same, so the limit does not exist. Right? Remember, the limit exists if and only if it's the same from all paths. Here we've displayed two paths where the limit is different. That's it. So showing a limit doesn't exist is usually relatively easy. All you need to do is find two different paths going to the same point, which give you different answers. But if you want to prove the limit exists, then there are infinitely many directions. How can we know we have checked everything? That's where the epsilon-delta definition plays a role. When we don't have a negative y squared in the bottom, this is a plus here, whereas this is a minus. So when x is 0, it's minus y squared over positive y squared, so negative 1. Carl is asking, so we can say that as we go higher in dimension, it gets harder to find a limit that exists. No, because it's going to be the same definition, right? The definition I wrote down extends to higher dimensions immediately. It's valid in 3 and 4D, and it's just as easy. To verify a limit like this, then we cannot prove it. We have to try and disprove it. Well, I mean, What you're going to want to do is convince yourselves. You try a few paths. If you get different limits, limit does not exist and that's it. If the limits are always the same, then you start thinking, well, maybe the limit does exist, and then you have to prove it. Let's take another example. xy over x squared plus y squared. Still going towards the origin. Renji is asking, when we say the limit is equal to 1, does that mean 1 on the x-axis? It does not. What does it mean? It means 1 on the z-axis. Right? Remember, what are we looking at? We really have a function z equals f of xy. So if this is approaching 1, it's the z value which is approaching 1. Brune is saying you can only check 2 paths here. What if we are in higher dimensions? Well, I mean, we in this particular example, we only checked 2 paths, and that was sufficient for us because they turned out to be different. If they were equal, there are still many paths to check, right? There are infinitely many different paths to check. So, I mean, of course, we're not going to spend our whole lives checking infinitely many paths. After you've checked enough, you need to convince yourselves that the limit does exist, and then you have to prove it. Consider this. Let's repeat the same idea, right? We're going towards the origin. We are going towards the origin. Let's have a look at what happens on the x-axis. So Brune is saying we could check 10 paths before seeing it as different. How would we know when to stop? Exactly. You don't know. Nobody knows. And plus, are those 10 paths you chose, are they good paths? Or were they really 10 of the same path? That's the thing. So, I mean, at some point you get tired of checking paths, hoping for different answers when they all turn out to be the same. So then you have to prove it. We'll take a few examples. So it is a function z equals 1 or a straight line parallel to the z-axis. Not a straight line. When if z is equal to 1, what is that the equation of? Here. So, Carl, thank you. This is the equation of a plane. So it's really a plane. Z equals 1. Here, if x is, so we're looking on the x-axis, if y is 0, what is this function? If y is 0, the denominator is x squared, the numerator is? Numerator is 0, so the function is 0, so the limit is 0. If the limit exists, it has to be 0. repeat on the y-axis, right? If we're going towards the origin on the y-axis, if x is 0, what is the function? If x is 0, the denominator is y squared, the numerator is 0, so the whole limit is 0. All right, same as before. Maybe the limit exists. Maybe it doesn't. I mean, all we did was check two paths. That's not enough to really convince ourselves. Let's try a different path. Let's try going towards 0 from the line y equals x. Let's see what happens. If y equal to x, if y is x, what is this function? If you replace y with x, you get x squared on top. And on the bottom, you get x squared plus x squared, which is really x squared over 2x squared. These cancel out, and you get a limit of 1/2. And now you're in trouble. We had two paths giving us a limit of 0, but now a third path gives us a limit of 1/2. Limit does not exist. Shen is asking, can we choose y equals 1, right? But y equals 1 is right here. And we want the behavior as you're getting closer and closer to the origin. So y equals 1 does not approach the origin, does not go through the origin. We don't want to choose that. Quinn is asking, is it a plus at the bottom? Right here, it is a plus, x squared plus, I mean, the original was x squared plus y squared, right? And we're just replacing x with y. I'll try to write bigger. Let's try another one. I said I was going to write bigger, but that's not really bigger, is it? So Shen is asking if it has to be a path through 0, 0. It absolutely does, right? We're looking for the behavior as x, y goes to 0, 0. So we absolutely need that. So same thing here, right? We're still going towards the origin. I mean, of course, this idea can be adapted to any point A, B. Here we're using the origin for simplicity, but there it is. If x is 0, right? If we're doing it on the y-axis, what is the function? When x is 0, numerator is 0, denominator is y to the 4, whose limit is, of course, 0. On the x-axis, if y is 0, this is 0 over x squared, whose limit is 0. So, you know, they agree. Looking good. In the previous example, we had tried y equals x. Let's try that again. See what happens. And when y is x, if y is x, this is x cubed. And the denominator is x squared plus x to the 4. Finite is suggesting the degree of the denominator is higher than the degree of the numerator. Doesn't it make it undefined? Maybe. Can you give me a path where we're going to run into trouble? Here, you see what's going to happen, right? We can factor out an x squared from the bottom, and you get 1 plus x squared, and these cancel out, leaving you with still a limit of 0. Shen is suggesting, what if you took the path y equals x squared, right, and convince yourselves, you know what that looks like. This does go through the origin. So if you take y equals x squared, what happens? You get a x, y is x squared, so this is x to the 4 over x squared plus y to the 4, so that is x to the 8. And if you factor out an x squared again, so this is x to the 5, this is x squared, 1 plus x to the 6. These cancel out, leaving you with a 3. Still a limit of 0, though. So that still gives you a limit of 0, but I didn't want to erase that. But now I think Aaron suggested a different path, namely square root of x, right? Which again goes to the origin. And if we use that, what happens? What did we have? We had xy squared over x squared plus y to the 4, which is x squared. Or, I mean, I think the suggestion was x equals y squared. You could do that. It's going to give you the same limit. Namely what? This is x squared over 2x squared, whose limit is easily seen to be 1/2 again. Perrin was suggesting 2x squared. I'll let you work that out. If you take a 2 here instead, I think it's only going to affect possibly the number coefficient outside here. I think you're still going to get 0. Try it, but I think it's still the same. But here, a different path gave us a different answer, and there you go. Limit does not exist. Well, if you need to say any polynomial for y, but you got to be careful, right? Any polynomial that goes through the origin. You have to make sure that it goes through the origin. All right. Consider this. Brun is saying 2x squared plus 1. The issue with that, if you graph that, you know what the graph looks like, and it doesn't go through the origin. So we're in trouble, right? We want the behavior for values close to the origin. This does not get close to the origin. You need a function going through the origin here. All right, consider this. Right, again, we're looking at the behavior for values close to 0. Let's try on the x-axis. If y is 0, what limit are we looking at? If y is 0, that's gone. Numerator is 0, so the whole thing is 0. If x is 0, for coming this way, if x is 0, you get 0 over y squared, whose limit is still 0. So on the x and y axes, limits are 0. Let's try on y equals x. If y is equal to x, this is 3x cubed. And the denominator is x squared plus x squared. So this is really 3 over 2x, whose limit is 0. So again, you know, if the limit does exist, it has to be 0. But we're still not convinced. What if we what if we looked at all the lines through the origin, right? All the lines through the origin have the form mx. where m can be anything here. Why don't we try that, see what happens. If y is mx, this is 3x squared mx. The denominator is x squared plus m squared x squared. And if you factor out, this is 3mx cubed. If you factor out an x squared, this is 1 plus m squared. X squared and x cubed cancel, leaving you with an x on top. Regardless of the line, the limit is 0. Shen is suggesting the highest degree is in the numerator, and it's bigger than the degree in the denominator, so possibly the limit exists. It's a valid suggestion. Let's try one more path. Let's try all the parabolas, right? Depending on what m is, it's steeper or less. What do we get? 3x squared mx squared over x squared plus y squared, which is m squared x to the 4. And then you can only factor out an x squared. From the bottom, you see what's going to happen, right? This is 3m x squared x squared. If you factor out an x squared from the bottom, 1 plus m squared x squared. One of them cancels out, but you still have the other to force everything to 0. You can try with the square root like we did the previous time, but you'll see that you get 0 as well. And at some point, is it valid if we set kx to the p and possibly find some value of k or p? Very nice. That will give you a different answer. Here, of course, you need p to be bigger than 0, right? Otherwise, it's not going to go through the origin. I mean, why don't we try that? It's a nice observation here. So Shen was suggesting y equals kx to the p for p bigger than 0. What do we get in that case? Limit as x goes to 0, 3x squared kxp over x squared plus k squared x to the 2p. Very nice. Very nice. You could always factor out an x squared, though. Well, I mean, that's actually going to depend on what x to the 2p is. If this is at least x squared, then you could factor out an x squared and cancel with that one, which would still leave you with an x to the p on the numerator. And if this is less than x squared, right, if 2p is less than 2, then you can't even factor out an x squared. So that would still leave you with at least x to the p and probably more coming from here. In every situation, though, it's easy to see that the limit would be 0. Regardless. Right? So on an exam, I would expect you to treat both cases if 2p is bigger than or equal to 1, or if 2p is less than 1. And convince the marker that both cases give you a limit of 0. What about when p is negative? Well, we made the assumption that p was positive. Because if p is negative, this will not go through the origin. And you need to go through the origin. So any of these curves yes, thank you. That's what I meant. Not bigger than or equal to 1, but bigger than or equal to 2. Thank you. Thank you, Shen. All right. Well, I mean, at some point you have to stop checking these paths and probably think that your limit is going to exist and is 0. Right? I mean, of course, there are still infinitely many paths we did not check, right? I mean, we did not check the sine function, e to the x minus 1, and, I mean, look, I'm not going to list them all. There are infinitely many. Ren is asking, how many paths do we have to check on the exam? Well, you have to check as many until either you get two limits that are different, or that you've convinced yourselves that the limit does exist. And then you have to prove it. You have to prove it using the Epsilon-Delta definition. So Quinn is asking, is there a way to prove this limit for all functions passing through the origin? Indeed, there is. That's where the Epsilon-Delta definition comes in. So let's prove it. We must show, let me just rewrite. Can we do an example? Well, yeah, we're going to prove it right now, right? Because we took different paths, we got the same limit. And we keep getting the same limit no matter which path we're trying. So at some point, we got to give up on that path. Terrible pun there. But we have to give up trying to find a path that gives us a different limit and just conclude that the limit does exist, and now we have to prove it. So Quinn is asking, if we're looking for a limit as x, y goes to 0, 1, we have to use functions that pass through x equals 0, y equals 1. Exactly that. Is the limit ever touched, or does it simply tend towards the limit? Well, that depends on your function, but it's, right? In the limit definition, you are getting closer and closer to the origin without ever reaching it. Ren is asking, what if you went straight to the proof? Well, what if, I mean, if you go straight to the proof, you're not going to be able to prove it. And Tony is asking, why don't we use epsilon-delta at the beginning? Well, I mean, you have to be sure that the limit does exist, because you might be wasting your time with the epsilon-delta definition. It's much easier to prove a limit does not exist by finding two different paths which don't have the same limit than trying to prove that it does exist. Ren is saying, will the proof not be undefined if the limit does not exist? It's not that it's going to be undefined, it's that you're not going to be able to prove it. But just because you cannot prove it doesn't mean someone else cannot prove it. And then you don't know. Is it just you that is not good enough with the proof, or is it that the proof doesn't exist? And then you cannot answer that question. Prin is asking, if we have 5 variables, it follows the same principle that the function has to pass through these points. Exactly that. Phi is asking, is 1/2 really 0.5, or does it tend to it? It's really 0.5. So what must we show? Did you write that down? We must show that if epsilon greater than 0 is given, there exists a delta greater than 0 such that if your point xy is close to 0, 0, then your function minus the limit should be less than epsilon. Vinit is asking, what if we take a function which is not differentiable at 0, 0? That doesn't matter. We haven't discussed differentiability yet, and whether or not a limit exists, well, I mean, of course, if a function is differentiable, you know that it had to be continuous to begin with. And although we haven't defined continuity in higher dimensions, you certainly expect that to be the next thing. So, yeah, big buts. Let's not discuss that quite yet. Let's just say, let's not say anything. Let's not worry about differentiation right now. We'll discuss that at maybe tomorrow. So we should be finished in about 20 minutes. Stick around and we can discuss. Yeah. So look, I mean, this is what we need to prove. So let's start with that. Let's start with this absolute value. I mean, the minus 0 is not playing a role here. So that's what that is. And you know that the absolute value of a product is the product of the absolute values. The denominator is always positive. 3 is positive. X squared is positive. So this is really 3x squared absolute value of y over x squared plus y squared. Very well. Well, now, look at this x squared. It's essentially half of the denominator. If only you had a plus y squared there, you could cancel everything. But y squared is something positive. So I'm going to add a y squared. I'm adding something that is bigger than or equal to 0. So I'm making the whole thing bigger. And now, wouldn't you know it, now you can cancel, leaving you with 3 times the absolute value of y. But absolute value of y is just the square root of y squared. And I'll do exactly the same thing I did before. I'm going to make this bigger by adding a positive quantity, namely the x squared. But now look at this. This thing, again, the 0, 0 doesn't play a role, and the norm of xy, this thing is really square root of x squared plus y squared less than delta. My goal is to make this less than epsilon, but this is less than that. So you see what to do now, right? If you take delta to be, what are you going to take delta to be to make this less than epsilon? You're going to take delta to be epsilon over 3, so that this is less than, the 3 stays there, this is less than epsilon over 3, and you're done. This thing is made less than epsilon if you choose delta to be epsilon over 3. That's it. You have shown that you can choose a delta, namely epsilon over 3, such that if this is less than delta, then that is less than epsilon. So the limit exists and is 0. The limit is 0. How are we doing? Questions here? Anybody? We're good? Why do we have to multiply epsilon by 3? Well, I mean, the 3 is already there, right? So we have no choice. It just carries along. Here we were not multiplying epsilon by 3, but taking epsilon over 3. Well, I mean, I'm saying if we choose, right? Because this thing, 3 square root of x squared plus y squared, square root of x squared plus y squared was less than delta. So here we had less than 3 delta. But what we want is not 3 delta, we want epsilon. So if you replace delta with epsilon over 3, you're good to go. We have no choice as far as epsilon is concerned. Epsilon is a given fixed value. We do have freedom as far as the delta is concerned. Exactly as Shen suggests, our goal is to prove that f of x minus L in absolute value is less than epsilon by choosing a good value of delta, by showing there exists a delta, which leads us to that. Maya is asking if we can explain why xy is less than delta. Well, that's just the definition, right? That's the definition. Let's look at a graph of the situation here to understand what happens. Right here, in fact, we're at the origin. Well, I mean, it's going to be a terrible example. Let me do it in general. We're saying that if you have some function hovering above, and if this is the point AB, we're saying that as x and y get close to AB, the function should be close to some limit L, meaning that if you take any point xy in the disk of radius delta, then everything should map essentially to some cylinder. Everything should get mapped inside here. That's what we're saying. You are not picking your own epsilon. Epsilon is fixed. Epsilon greater than 0 is given. You can pick your own delta, though. You have freedom with respect to delta, not with respect to epsilon. Is there a set method to use to change the form of the function to fit the inequality? Of course there is not. There is not. You have to adapt. But why does that mean that square root of x squared plus y squared is less than delta? Well, in our case, AB was 0, 0, right? So the point xy minus the point 0, 0 gives you the vector xy, and the length of that is the square root of x squared plus y squared. Right? This is that. It's the length of the vector. That's why we were looking at linear algebra yesterday. What section of the textbook did we cover today? I don't know. Page 947 and afterwards. All right. So what are we doing? We have introduced the concept of limits. We have extended the concept of limits to higher dimensions, and everything, all the properties of the limits from Cal 1 extend to higher dimensions. What am I talking about? Limit of a sum is the sum of the limits if both limits exist. Limit of a product is the product of the limits. If both limits exist, limit of a quotient, same thing. Squeeze theorem applies. Everything essentially has its extension in there. Carl is asking, so the radius of the circle is delta? That's correct. And after the definition of limits in Cal 1, we use that to define the concept of continuity. And let's do that here. Definition. The function f of xy is said to be continuous at the point AB if the limit exists and is equal to the function at that point. Exactly the same definition as in Cal 1. And using properties of the limit, properties which extend from Cal 1 again, let me state it as a theorem. I won't prove it, but polynomials in x and y are continuous. Polynomials in x and y are continuous everywhere. Rational functions, one polynomial in x and y divided by another polynomial. Exponentials, in one variable you know to be continuous. And compositions. Of continuous functions. Products, quotients, and so on and so on. Let's take an example. Let's discuss the continuity of this function. Well, from Cal 1, the function sine of t you know to be continuous. Right? You can draw that without lifting the pencil from the paper. Here, g of xy, which is x squared plus y squared, is a polynomial in x and y. So that's continuous. consequently, the composition of these two things is going to be continuous by that same theorem. So the composition is continuous as well. There it is. After limits and continuity, you know what we did in Cal 1. We used the definition of limits to define the derivative. We're going to do exactly that tomorrow. We're going to use limits to extend the notion of differentiation to functions of several variables. We'll see that tomorrow. Questions? How are we doing? Anybody? Brun, we should stay away from Maclaurin series in higher dimensions for now. If you have a limit of xy going to the origin, and if your function is just a function of x, it's really just a limit in terms of x. So there's no y there, and you're good to go. What will be in the midterm? Certainly everything we did so far, but I really wanted to do differentiation. We'll see what we do tomorrow. I still haven't written to the midterm yet. We'll see. Right, Bryn is asking if that was just in the numerator. I mean, look, these questions could become very, 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 very difficult. I'm going to suggest if you have a denominator of x squared plus y squared, and you already have an x squared there, you might try to do, I don't know, it's difficult to say. You might try to do the trick we did originally. Yeah. Pryn is asking, why can't we use these special series in higher dimensions? You can. Nothing wrong with that. Nothing wrong with that. In fact, as I suggested, we're going to see Taylor series in several variables. So, I mean, look, if it works, because you did just have a function of just x in the numerator, so that might work. Etienne is asking if you will have a practice exam prior to the midterm. I was not planning on doing that. Can we use complex numbers for a firm base to prove if relevant? You shouldn't do that on the exam. Vineet, correct me if I'm wrong, but I think you're not registered for this course. So if it's not for our exam, there's no issue. And using complex numbers sometimes makes things much simpler. Shen was asking from previous question, the series 1 over n ln n squared, starting from 2 to infinity. Find the terms that give the sum to within 0.01. Does the starting point of the n matter? It does not. Of course, you don't want to start when n is 0, because you get a 1 over 0, which is an issue. And if n was 1, ln of 1 is 0, so you still get a 1 over 0, so you don't want that either. So that's why they're starting this at 2. In general, it doesn't matter where you start. You know that, yeah. I mean, it only matters in the sense that the approximation will be different, but whatever, right? And by that I mean if you had 1 over n cubed starting at 10, I mean, you could have started this at 1, 2, 3, 4, 5, 6, 7, 8, 9. Doesn't matter. If they're asking you to approximate this, then that's what they want you to approximate. Are we going to use integral to approximate? We already did. We did that. So you are certainly welcome to do that. I mean, especially in situations like these where your series is not alternating, integral approximation theorem is very useful. Absolutely. Thank you all for coming. There were questions that somebody was going to ask me after class. Did that student leave already? Well, I mean, of course, Shen, if you get a k which is less than 10, if you're starting from 10 onwards and you get a k that is less than 10, you're probably going to want to adjust that. Absolutely. Absolutely. Very nice. Yeah. If you need, you can go ahead. Math 180 will give me an answer to the different infinities, and indeed it will. A very nice answer. It's a very nice part of the course. And as you may know, Math 180, it's just an elective. No math background is assumed. So already having done calculus 1, 2, and 3, you will have a nice advantage over everyone else, and you should get an excellent mark in that course. Can we do -1 to the n, square root of n plus 1 minus square root of n, like this? Shen is asking. Tony, apparently we're in chapter 12.6. That's what somebody else suggested. I had given the page number as 947. But essentially, if you look up limits in higher dimensions, that's where we are. Test convergence and divergence of this business. Let's do it. What I would do, I mean, look, you're thinking to yourself, maybe telescoping sum. The issue is that it's not really because of this -1 to the n. What I would do is I would multiply this by the conjugate. So square root of n plus 1 plus square root of n over square root of n plus 1 plus square root of n. You're multiplying by 1, you're not changing anything. And this becomes n plus 1 minus n over square root of n plus 1 plus square root of n. These n's cancel out nicely. And now you just get this nice thing. You just get this nice series. And for large values of n, this positive 1 doesn't really play a role. So the denominator is like a 2 root n. So, I mean, it is a series with both positive and negative terms. So two questions arise naturally. Does it absolutely converge? So we're going to test this series, which we're going to test using limit comparison with the series 1 over root n, which is a divergent p series, where p is 1/2 less than or equal to 1. And so do a limit comparison, you'll see that series diverges. I won't do it here, I'm sure you can do that, no issue there. And then, so it does not absolutely converge. It may still conditionally converge, and then try the alternating series test. So it does conditionally converge using the alternating series test. Vinita is asking for long division of numbers or polynomials. I know both, absolutely. Well, I mean, I assume you're referring to the usual long division. Right, like 825 divided by 5. So how many times is 5 going to 8? It goes in once. And then 5 into 32 goes in 6 times. Subtract. I mean, maybe if you learned it the European way, it's the other one, but polynomials like 1, sure. So it's 1 divided by 1 minus x. Sure. Or, well, I mean, depending on where you're going with this, right? So, I mean, here there's going to be a 1 over x. And then you get a 1 minus 1 over x, and then you subtract, you get a 1 over x. And then you'll have 1 over x squared, and so on and so on. Is that where you're going with that, or were you going somewhere else? Was it 1 minus x, right? So if you multiply by 1 minus x, if you subtract, you get an x, and then x minus x squared. If you subtract, you get an x squared. And so you see, right? I mean, here you get a nice result, the nice geometric series result. Is that where you were going with that? 1 minus 1 over x is really 1 plus x squared, and so on using long division. No, not that. All right, very well. X is y plus 1. Okay. So, no, I'm not sure where you're headed with that. But this is a nice observation, right? If you do long division, 1 divided by 1 minus x, you get this nice series F. If you take x plus 1 minus 1 altogether and treat x plus 1 as a single variable, fine, sure. Yeah, Vineet, I'm not sure where you're going with this. Well, let me think ahead. And perhaps you're saying that 1 over x can be written as 1 over x plus 1 minus 1, which is 1 over minus 1 plus, it's the x plus 1 you want to group together. And if you factor out a negative, negative 1 over 1 minus x plus 1. And so this gives you, again, it's a geometric series, negative x plus 1 to the n. Well, I'm not sure what polynomial you're referring to related to the Riemann zeta function. I still don't know what polynomial you're talking about. You say we can divide the polynomial assuming x plus 1 to be a single term. I mean, I'll believe that. Are you talking about the polynomial x, which you're treating as x plus 1 minus 1? And you want to divide that by x plus 1? Maybe it's best that you write this out on paper and send it to me by email. You have my email. I gave it to you last time. Right, this 1 over x. Yeah, so let's do that. Write everything out on paper, take some pictures, send it to me. We can discuss this by email. Questions in the meantime for everybody else? Anybody else still here? Questions? No? If there are no questions, we'll pick this up again tomorrow. Thank you all for coming. and I'll see you tomorrow.